Okay, so this is the Mod 5 video part 1. There will be 2 parts to Mod 5. I think, I'm pretty sure. This is the last mod. Now, this is kind of like, you know how like school doesn't get rid of stuff that it probably should. Admittingly, I'm somewhat guilty of it. This is sort of old school stuff. It's called nonparametric statistics. Um, and part of me is like, should we really even be teaching these anymore? Non-parametric essentially means that you're not using a continuous probability distribution. So you're not working with like a normal distribution or a chi-square distribution or an F distribution, which all of our prior tests and work that we've done in this course has done. To be honest, non-parametric tests are somewhat Mickey Mouse. They're sort of based on heuristics and calculating statistics, typically calculating things based on ranks. And literally ranks means like first, second, third, fourth, fifth. Like if you think about like how people do like in a race or something like that, say, 5 people with marathon Monday tomorrow, because I'm doing these videos a little early, but say, and literally it's based on ranking first, second, third, fourth. And ranks are not numbers. Ranks are just like positions. We're not accounting for like the actual timing of things, we're just counting for like, first, came in second, came in third. That's what a rank is. And so non-parametric statistics are primarily based on ranks. And they have no assumptions about the data. Now, the advantage to these is they always work. The disadvantage is they're not very robust tests. You do not use them if you can use something else. The only very legitimate reason to have these in this course is because when we don't have a sample size of 20 or greater, we generally don't want to use the other tests that we've used in this course. And you're like, well, when will we have a sample size that small? And the answer is in psychology. So this may be like the one realm of the universe where it is still somewhat sensible to actually teach these, because you may end up in like a clinical research kind of thing with a really small like therapy group or something like that, and you still want to be able to do some statistics and some formal mathematical like formalities to test things and work on things. And non-parametrics do give you that option. So therefore, they are the one legitimate reason for using them. In this day and age of computers, it's not, people will not, as a first priority, use non-parametric statistics. But that's what they are. Now, what they are essentially is we have a method that parallels all of the other methods we use for this class. So in a sense, this is actually your final exam review as well, because Mod 1 was means testing. Mod 1. Okay. Mod 2, correlation regression. Mod 3 was chi-square. Now that actually we are not going to have a non-parametric version of. So this one we're not going to essentially review, but it was only a couple weeks ago. And then Mod 4 is ANOVA. As I do this Mod 5 stuff, these 3 mods, Mod 0 is not on your final, so don't worry about it. So Mod 1, Mod 2, and Mod 4, we're going to essentially review with non-parametrics because there are non-parametric versions of the material in these mods. So in other words, for means testing, there's an alternative for when you don't meet the normality assumption or don't have a sample size of 20. For Mod 2, there's a correlation non-parametric method that we can use when we don't have quantitative continuous data. We can do it on ranks and ordinal data. Chi-square is the one thing we're not going to actually cover, but don't forget, chi-square is based on categorical data, so it's a little different anyways. And then ANOVA, we're going to cover something in a few minutes called the Kruskal Wallace test, which you don't have to worry about the assumptions of normality and other issues that you would have. And you can use it on really small data sets. So in a sense, this is actually your final exam review in a way too. Okay. So non-parametric statistics, part of me is like, they're sort of Mickey Mouse. They're way easier. They're actually really simplistic, and you're going to see this. So there's not that much to this, especially after doing all the other stuff in this class. Then you get to this and you're like, this is easy. Yes, it is. So I have for you these 2 videos. There will also be for you a test on Canvas. I only count 4 out of the 5 tests. This is the 5th test. So if you have 4 test scores that you're satisfied with, you don't really have to take this test. I'll enter a 0 if you don't take it, but that won't count because it will get washed out. I will not until the final exam, like literally the day of the final, I will do the grade adjustments, meaning um, I'll drop one formal test, perhaps a problem set too, but that's kind of up to me. I don't have to. Technically, I don't have to drop a test either, but typically I do just because with 5 tests, so 4 of the 5 count for your grade, which means that you don't necessarily have to do this mod 5 test. It's there for you. A lot of people do it because it's really easy, but in wariness, I don't know if that's a word. It is the end of the semester. People are busy. There's a lot of stuff going on, especially if you have classes and stuff. And so taking another test is like maybe a burden to you. You do have to take it if you missed one of the other tests. For the online class, it's probably not. I don't know if anybody in the online class actually missed a test. Perhaps I don't know. I forgot. But yeah, so that's the deal with that. Anyways, so what does non-parametric mean? It means no probability distribution. So there is no like, when we do regular ANOVA, we assume that the data are normally distributed and that there's a normal distribution underlying the data. That assumption does not hold for non-parametrics. So they're not as powerful. They're sort of statistical tests. I mean, are they real statistics? I don't know. They're older. I mean, this is stuff that like you could do, without a computer fairly easily and stuff. I mean, to be honest, to some extent, I kind of think of them as things that I don't know exactly how they made some of these up. I took an entire grad course actually in non-parametric stats at one point. It wasn't that interesting. But they're not as powerful. They're not something that you would use if a regular test can be used. In other words, if you have a sample size greater than 20 and your assumptions hold, you would not use non-parametric stats. But if you have a small clinical trial and you have like 10 samples and you still want to publish something and get a paper written and do some statistics on it, non-parametrics are your go-to. Or if you have data that is egregiously distributed in a way that is not, you can't possibly meet a normal distribution no matter what you do, you still have the option because it wouldn't be valid. Like it's your data is like, maybe your data is like this or some like weird like double by, so you couldn't possibly justify using a regular test, and you can actually you could still use a non-parametric distribution method because it would still be a valid statistical test, whereas the normal one wouldn't. Okay. So let's work backwards. We're going to actually start with the non-parametric equivalent from mod 4, the non-parametric equivalent of ANOVA, and then we're going to go do the correlation regression one. This will be the first video, and then the second video, I will do the means test. Okay. So the mod 4 was ANOVA, which of course it was only last week, so I don't know how you could have forgotten. ANOVA is to compare multiple means. Okay. So the null hypothesis in ANOVA is always that the means of usually 3 or more groups, but you could actually do it, are equal. So that's the null hypothesis, and you're always testing against that. So you're doing the same thing here. The hypothesis is actually going to be the same. But analysis of variance uses the F-test, and the assumptions are that things are normally distributed and that the population variances are equal. This is actually, I probably didn't mention this enough in ANOVA, but what you can't have is like males and females, and like the standard deviation here is like 500. I'm going to grossly exaggerate this. And the standard deviation here is like 10. Standard deviation variance, of course, are related. So you can't have like an egregious issue like this. So that actually might be a case when you might want to go and use the non-parametric friend of ANOVA called the Kruskal Wallace test. I have no idea who Kruskal and Wallace are. You're going to see a lot of people's names in these non-parametric things, but I don't know who these people are. I used to know. I think their pictures were in a book at one point. Anyways, so I hope I didn't just muck up my video. But anyways, so you are going to see that. So let's look at this. Now, here's data from Blumen chapter 13. Again, we keep Blumen because the material's in there. Once again, we have Mickey Mouse sized groups. However, in this case, that's fine because we're doing non-parametrics. So a researcher wants to see if the total number of infections that occurred in 3 groups of randomly selected hospitals is the same. So we have group A, group B, Group C. I'm not quite sure what the concept of a group of hospitals is, but okay. So we'll assume that this is like 4 different hospitals in Group A, 4 in Group B, 4 in Group C. Okay. At alpha equals 0.05, is there evidence to reject the claim of the number of infections being equal? So again, we're looking at an equal means this is the same hypothesis as ANOVA. We're looking for whether or not the average number of infections is equal for the 3 hospitals, and this is the data. Cool. Okay. Now, this is from Blumen, of course. Now, these you actually could do by hand, or you could look them up in the funnel tables. SPSS does do these, so we're just gonna use them in SPSS. I believe Blumen actually still has these tables. So what you do is you rank things, and you're like, rank, what does that mean? Literally you rank things and you rank them across the group. So what you do, I hope I show this somewhere, is here. Okay. And you're like, what's this? Okay. Look at this carefully. So the lowest infections is 80, which is B. And so every data value is assigned a rank. So what this table is doing here, let's go back and forth, I should put it, is taking this data and just taking all of the data and it's doing like group and then like data and then like rank. Okay. So the lowest one is 80, and that's group B. And so that's going to be rank 1. The next lowest one is 110, I think, and that's group C. And then the next lowest one is, oops, 105, sorry. The next lowest one is 110, excuse my mess, but that's still group C. And so on and so on. So what it's doing is taking this and redoing the table, and then you have this rank column, okay? And that brings us to what the heck this test is operating on. So what it's operating on is R1, R2, and R3. This is actually for group A, B, and C, and it's like the ranks, the sum of the ranks for the kth group. So it's taking like this here, and like for group C, it's going to add up like 2 plus 3, and then whatever other ranks are group C, there'll be 2 more of them, and it's adding up the sum of the ranks. I don't know whoever thought of this, but it works. It's really something that like you could almost do this like on a paper napkin, at the bar, you could sit there and do like rank-based statistics. So literally just make this table and just add the ranks for each group. That's what this R1, R2, R3 thing is. N1, N2 is just the number. So that's just 4, 4, 4. That's just the sample size in these groups. And then you just manually calculate this H statistic. I don't know why it's called an H statistic when it's the Kruskal Wallace test. Strikes me as it should be KW, but it's an H statistic. And it's just an algebraic formula where you stick all the numbers in and calculate it, and you get this H number. That's all you have to do. SPSS is going to do that for us, but it's pretty easy. But then when you get this H number, what do you do with it? Like, how do you determine whether it has, because we're still operating on the p-value less than 0.05 thing. So you just take the ranks and the sample sizes and just add everything up. And I don't know where this formula came from. I don't know. Like, it's amazing that people just came up with this stuff. It's legit. It works. But okay. So you do all this, and apparently from here, this is the sum of the ranks for group A, group B, group C. This is what I was talking about here. This is the stuff. So you're summing up the ranks, and then you're sticking all the big numbers into this formula, which they didn't. So they actually do show you the algebra, believe it or not. So they just take it all algebraically, and they get 5.346, and you're like, that's nice. I know. What does that mean? Somewhere there's this voodoo table that you can look all these up in. Now, we're going to get this in SPSS, and the only thing we care about is that if the P is less than 0.05, there's a significant difference between the groups, and that means that we that we reject the null hypothesis. Because the null hypothesis is that the groups are equal, and the way that we're testing the mean equivalency of the groups, you can kind of correlate this, though. It does kind of make sense that the ranks, like if the group's means differ a lot, then the ranks are going to differ too. So that's how it's being done. And then you just want to determine whether or not the p-value is less than 0.05. Now, if you're just given this 5.3416, it doesn't even like this is not from a distribution, so you can't even get a sense of like where it actually physically fits on a distribution like you can with the normal. I mean, everybody in this class knows that a 5 on the normal distribution is going to give you a really low p-value because it's way the heck out there. But there's nothing to draw because there is no such thing as an H distribution. That's why these are non-parametric. Somehow it is all programmatically in SPSS, and then there's also these tables. I used to know all this because I used to be smart, but this is not like something that I immensely care about these days. But somehow, there's a table with critical values, but we're just going to run this in SPSS and get a p-value. And somehow, despite the fact that it not being a true area under the curve situation, SPSS does in fact have p-values, and we're just looking for a p-value less than 0.05, and then we reject our null hypothesis. And if our p-value is not less than 0.05, we would fail to reject our null hypothesis. Now you can kind of see just from the sums of the ranks here, you can kind of see that these are kind of like pretty far off. Because they're not, if the means were equal, then you want the ranks to be like kind of even too. They're not. Like the sum of the ranks is 39, 23, 16. But who knows? Not me. And I forgot the answer despite the fact that I watched the video that I made last year a few minutes ago. Anyways, so that is a test, and then you want to make the decision. In this case, apparently the critical value is 5.991. And that's going to give us a p-value not less than 0.05, not by much. And so we will not reject the null hypothesis. Now, these are not very robust tests. To reject a null requires more like substantive data than this would probably be a p-value less than 0.05 if it were regular ANOVA, but it's not. So in this funny way, it's not going to detect a difference at this level. But let me show you how to do this in SPSS, because that's what inquiring minds want to know. So I have the data somewhere. I looked at it all and I lost it all. How about that? Yeah, okay. So I have it here. Okay. Yeah. So this is the hospital infections data. I'll put these in your dataset dump just to make sure they're in there. They'll be in the Canvas folder that I just put all the data in because it's so much easier than organizing it one by one. There'd be like 500 extra rows in Canvas if I didn't do that. So I'm opening SPSS and getting the hospital infections data. The old videos, which are these guys, are still actually up on Canvas, but I want to run this again sort of live for you so you can look at it. My SPSS is very, very slow. It's not doing anything. It's just sitting there. Okay. Now it's got like an hourglass on it. I guess that's like an improvement. That was interesting. Okay. Let's hope I have some data here. Wow. Sorry about the silence, but I don't know what SPSS is doing. It doesn't seem to like me. Okay. Where is SPSS? There it is. That was like the world's slowest opening of SPSS. Anyways, this is the data. This is in fact the data. These are the three groups, A, B, and C. This is this infection rate thing. Now, I, as usual, had initially entered this as a string. And when you initially enter things as a string, you need to do the automatic recode and get the numeric. I already ran it in here, but you need to run that automatic recode as explained many times now and get that. So if you only have the string column here and not this, you need to go under transform, automatic recode, and do this and like recode it, and then it's going to do that like number thing so that you can actually do that. This is really like old school. I mean, I don't think in the last 15 years any software that's new has had to do this, but a lot of SPSS stuff. I mean, SPSS has been around for 50 years, people. I mean, it's like my age. I'm older than that. But yeah. So you have to get this column here because you have to have it coded with that like numeric label coding and not like as a string. But how do you actually run this thing? Okay. So it's under analyze and it's under way down under nonparametrics. A lot of our stuff is going to be under here, and they hid it. It's hidden under. I actually think this will work too, but I'm going to go under legacy. I'm going to go under K independent samples. That's how I know it. I think this one might actually be the same, but I don't want to play too much of the video. So K independent samples. This is what we want to do. Let me do that again. Analyze nonparametric test. I think this one right here will give me the same result, but I don't want to. I don't want to try it. Under legacy dialogues, legacy meaning old. K independent samples. This is going to do it for us. Yes, it is. Okay. And so the only variable that appears for grouping is the T variable. The old string variable doesn't. So we want to go to our grouping variable and we want to go to define range because SPSS doesn't know that. It's coded from 1 to 3. So 1 is the min and 3 is the max. Those are the values that automatic recode gives us. And then the test variable is infections. And then all I have to do, Kruskal Wallace is there. There's actually these non-parametric tests. There's like 10 million people that like take ownership of them. I think like every statistician in the country in the 50s and 60s had their own non-parametric test. Anyway, so it's all set up to go, and I hit OK, and I get this. Yay! And this is what we get. So these are the mean ranks. Now the mean ranks are not quite the same as the sum of the ranks, but they're just the sum of the rank divided by 4. So going back to this, these were, so 39 divided by 4, that would give me a 9 point something. So that would be the mean rank on that. So that's what I would see. So yeah, 9.75. So these are the mean ranks. And then we have here that H statistic. I don't know why it's called an H statistic when it's the Kruskal Wallace test. I don't know anybody named H involved in this, but it's 5.346. That's the number that we got from, or we looked at because that's this number that you get algebraically by using the big formula. But then very importantly, and really the thing that we most care about is we have an asymptotic significance, otherwise known as a p-value. There's some kind of like mathematical voodoo simulation of, I think, a chi-square distribution that actually gets this somehow. I don't know. I forgot. But the p-value is 0.069. It's not less than 0.05. So just by a sort of like slight margin, we do not reject our null hypothesis. And we conclude that we can't, based on this data, conclude that there's a significant difference in the mean number of infections for the 3 different hospitals. Because it's a small sample size, limited case, and we can't make a conclusion like that. So that is how you run and interpret this. And look at how simple this is. Like, this is the whole output box. I mean, compared to the stuff we looked at before, it's like, wow, okay. So that is the Kruskal Wallace test, which is the non-parametric equivalent of an ANOVA test. So buzz through that really quick again. We would run this if we have small samples or if we have some egregious violation of normalcy or equivalent variances. This is, of course, small samples. It's based on rank. So you look at the data and you rank it, and then you calculate for each group. Like for B, it would be 1 plus 4 plus 8 plus 10, which I lost track of what I was doing. I'm too old for this. 23 divided by 4, so the average rank would be like 5.75, and then the sum of them would be that, and then that's where you get these from. Okay, so 23, and then you stick them all in this magic formula that I have no idea where it actually came from, and then you get this H statistic for the Kruskal Wallace test. But then you can determine a p-value associated with this, and in this case the p-value is 0.069, which is not below 0.05, so we conclude that there's no significant difference in the mean of the groups. It's magic. Okay. That's all there is to the Kruskal Wallace test, and that's all I'm going to give you. Just simplistically, to be able to run a basic, we're not going to do two-way ANOVAs and reactions or anything with this. I think you probably can do a two-way ANOVA somehow, but I mean, these are tests for like really simplistic things. They're not going to be like really challenging. Anyways, so that's the first one. The second one that I'm going to get in this first video before I split, I'm going to split the video and do the other two, the second video, if that makes any sense. There is no mod 3 stuff in this. Mod 3, the chi-square, is the one thing that is not in the non-parametrics because it's sort of non-parametric to begin with anyways. It's based on categories. But mod 2, going back to correlation regression, the only thing we're not actually gonna do regression, but we're gonna talk about this thing, the Spearman rank correlation. It is a non-parametric equivalent to a Pearson. Very importantly, this can be used with ordinal data, such as ranking, first, second, third, which ordinal data, remember, is not really numeric, it's rank data, like cold, warm, hot, okay? So you can actually, remember, of course, a correlation is between two variables. So we're only going to look at a bivariate correlation here. But if x and y were like, if x were like first, second, third, and y were like medium, cold, medium, hot, is that what I said before? I don't know. You could actually do a correlation on your ordinal data, which is actually pretty cool. Okay. So that's why I'm showing you the Spearman rank correlation. Okay. Similarly, like the other one, all of these non-parametric things are sort of done with these weird algebraic calculations, which I don't entirely. I literally took an entire master's level class as a doctoral level course too. There were like 4 people in it because who would be in a class like that? But I was in there. Hey, look, and the whole book was kind of like full of these kind of like little calculation things. But anyways, here is the example, which actually makes more sense than the blue stuff. A researcher wishes to determine if there's a relation between the number of branches and the total number of deposits. Now, this one, honestly, you could do this with a Pearson, so it's not really something you have to do with this ordinal Spearman rank correlation, but they probably couldn't come up with a better idea. So this is what they did. So this is the number of branches a bank has. This is like the type of like Bank of America, like in total type thing. And then the number of deposits. So you would think that more branches would be more deposits, but not necessarily, because banks could have like smaller, like they could be in like rural areas or something. But anyways, so you want to determine the correlation between this and this. Okay. And you really should do a scatter plot and look at it too, but I don't think they do that because no, they don't. But anyways, a sample of 8 banks is Sloan and the number of branches and number of deposits. Is there a significant correlation between the number of branches and the number of deposits? Okay. So the hypothesis, which of course is exactly the same hypothesis from mod 2, the null hypothesis is the correlation is 0. The alt is that it's not 0. Okay. Critical values, I don't think SPSS gives this anyways, but this is, of course, your cutoff value. But again, they have tables for these, which we don't have because we're cooler than that. I believe they're still in Blumen, but I have to tell you the truth. There's a copy of Blumen in my drawer in my desk at work. And I don't know if the tables are in there because I've never bothered to look them up because we have SPSS. It's way cooler. But anyways, once again, we have this rank thing going on. Now, these are actually 2, so they're ranking deposits and they're ranking branches. So the smallest number of branches has a rank of 1 and then rank 2. You see what these are doing? And so what we're actually correlating is not the original data, but the ranks, okay? So it's different than the way that a Pearson's done. Now, again, with this particular example, you don't really need this type of test for this, but so what the correlation is being done on is these ranks, okay? And the way this is done is these are the ranks, x1, x2, like it's just copying the 571. See, that's just copying that. And then you're actually doing the difference of the ranks. This is another thing you see a lot of in nonparametrics, subtraction people. So the difference in the ranks here is 0, and then like this minus this is 1, and they're squaring it to get rid of the negative and add to 0 thing. Same thing you would have like if you did the same old trick with the standard deviation where you can't have things that adding to 0. So we calculate d squared, which is this difference squared, and we get the sum of the d squared equals 12 thing. And that is part of this here little formula. And now we can actually get our Spearman correlation. Okay. 1 minus 6 times the sum of the d squared times n times n squared minus 1, where n is the number of pairs of data, which in this case is 8. And so now you have everything you need under the sun. You can just do 1 minus 6. And then the sum of the d squared is 12. And then it's over 8 times 64 minus 1. And so you get 1 minus 72. Oops, 1 is on the outside. So you get 1 minus 72 over 8 times 63. And then this would give you your R value, which I'm not going to calculate because I don't feel like multiplying 8 times 63. All right. Math professor multiply. 4 to 504, which I believe is the street address of the school, by the way. I think that's right. But anyways, if you just calculate this, you'll get this. So it's gonna be like 1 minus it's gonna be like 0.8 or something. I don't know. I didn't look at the result, but I'm excited. I think I got it. And so when you do all this, yes, you get this, and they did it here. So you get 0.857. And that is a Spearman rank correlation. But there's one problem. We have no idea if it's significant or not. Now, this is a pretty high number, but is the p-value less than 0.05? And the answer is we have to go to SPSS to figure that out because we're not smart enough. Okay. Again, there's tables. I don't really look through tables anymore. I'm way beyond that. It's 2025 people. And so we have to actually determine whether or not this is significant, even though it looks big and robust. And that's why we actually want to do these in SPSS. So how do we do them in SPSS? And the answer is this. Hopefully I didn't close SPSS because I don't want to wait for it to open again. But anyways, this data is banks, and again, I'll put this in your data dump for you. Don't worry, you can practice and play along, and you should, especially if you're taking the test. Even if you're not taking the Mod 5 test, I must warn you, these can be on the final. I don't think there's very many of them on the final. There's 20 questions on the final. I give you a data set and you answer questions about it. I think there's like 1 or 2 like really simple non-parametric questions. Let's see if SPSS opened my data. It did. Here's my bank data. Now, just to make you crazy, this one is entered as like XY, so it is correctly entered here. You don't actually need these, by the way. You don't actually need, in the old sample video, I actually bother to like recode those. You don't actually even need these. You just need the X and Y data because we're running a correlation. And all you have to do to run this correlation, it's super interesting. Go under Analyze. Like I said, we're kind of reviewing for your final because a lot of that is in here. So Analyze, Correlate. This one is not under nonparametrics because, I don't know, that's just how SPS organizes things. It's under Correlate, Bivariate, and we just do the 2 variables in here. But then we stop ourselves and we don't do Pearson. We check that off and we check Spearman. Okay, very important. Pearson is, I mean, technically with this data, you could just do Pearson. I don't know, but it's Blumen, it's a textbook, and they're using it as an illustration for Spearman, even though you wouldn't actually have to use Spearman for this, if that makes any sense. But anyways, this is how you do it. And this is just how you did all of your other correlations too. So it's like you're totally familiar with this. But just make sure that if I'm asking for a Spearman correlation, you check Spearman. And then hit OK. And down here we have, this is the last problem, not this one. So down here we have our correlation table, 0.857. We already knew that. And the p-value is 0.007. So yes, it's below 0.05. And we do, in fact, have a significant correlation between the number of branches and I don't know whether it was the number of deposits or like the amount. But anyways, that's the first part of Mod 5. There'll be a second part. See ya.